Swayam Prabha. Digital India. Educated India.
We have started doing analysis on boiling. So, last time we saw that how nucleation actually occurs. Now, let us now look at the bubble dynamics. Bubble dynamics. Now, in the case of a bubble dynamics, what happens is that there are two types of bubble dynamics that you can see. When the bubble grows, in quiescent superheated liquid, which is basically homogeneous. If you recall what is homogeneous and what is heterogeneous. So, this is one type, and when the bubble grows on a heated wall. Okay. So, this is heterogeneous. Okay. So, first we are going to look at what is basically homogeneous bubble growth. Now, if you recall the equation of continuity, what you will find. So, we are going to study this first. Okay. So, u we already know was a radial velocity in the liquid phase. If you recall the continuity equation that we did last time for a bubble inside a quiescent fluid medium, and we also know that rho v is much less than rho L. Okay. So, at the liquid vapor interface, this u at r comma t becomes equal to dr by dt. Now, integrate the continuity equation that we had equal to 0 equal to 0. Now, once you integrate it, okay, u r comma t. So, u r comma t will be equal to the growth rate. So, u r comma t will be equal to dr dt square. R is any arbitrary location in liquid phase. Okay. Now, the momentum equation for the surrounding liquid right. That is the momentum equation. Now, if you substitute this u r, where r is any arbitrary location as we said, if you use this u r now in this particular situation, okay, what we are going to get, let us see over here. So, this has been integrated, as you know, at the surface the velocity is this. Okay. So, it is very easy to show that the velocity progressively changes in that particular fashion. Once you substitute this into this equation, now what will happen is that Okay. That is the total momentum equation that you will get. If you integrate this momentum equation, this, okay, from bubble surface to r equal to infinity, that is in the far field, okay. Bubble surface is basically small r is equal to capital R, okay. You will get got it, okay. Now, so that is the equation that you get. Now we already know, if you recall the previous class, we already said that for bubbles with non-condensable phases, this was the total equation, right. If you recall from the last class, if the condensable phases are 0, non-condensable phases are 0, that goes away. So what we can do is that we can readily apply this relationship in the other equation. So therefore this becomes capital R d square r by dt square okay. So this equation is called the Rayleigh equation. Got it. So this equation is called basically the Rayleigh equation, all right, okay. So you can see that this is the growth of a bubble inside a superheated liquid, okay, and this is the general form of the equation that you will get. But however, there were some interesting findings that people noted. One of those findings were that during inertia controlled stage of bubble growth. So these are the initial stages, okay. One can conclude that the surface tension, which is given by 2 sigma by r, okay, is negligible, okay. And what you have is that your PV minus PL infinity is given as rho v HLV T infinity minus T sat that is the expression. So the initial condition so the initial condition over here is basically r is equal to 0 at t equal to 0, that is the initial condition, okay. So these are the two expressions that we see, that is, this is negligible and this is a function like this, okay. So now what we do is that we substitute, okay, this expression in this particular system, right, and we neglect the surface tension term. So using that, what happens is that the instantaneous, when you substitute that, it becomes dr square dt square plus 3 by 2, this two terms remains the same, okay. Now if you substitute the initial condition now, that capital R is equal to 0 at t equal to 0 is the IC initial condition. When you substitute that, the instantaneous bubble radius or bubble radius becomes okay. So, this actually tells you, if you look at it carefully, that this is a linear function of time. Right, or in other words, the early stage of the bubble growth, okay, it will predict you something like this, okay, T versus R, where the slope will be determined by all these quantities that you have in the bracket. But it is basically a linear function of time. This is the early stage of bubble growth for homogeneous nucleation. Okay. Now, during the later stages what happens? So, these are the early stages. During the later stages, we get slightly different situation, okay, during the later stages of bubble growth. So, what do you have in the later stages of the bubble growth? The inertial forces, okay, becomes insignificant. Okay. So, as the pressure PV minus PL actually goes down, okay, the interface, this leads to interface motion, okay, slows down. So, therefore, heat transfer, okay, becomes the process that limits, becomes the process that limits, okay, that limits bubble growth. Okay. So, it is like the not an inertial dominated framework anymore, it is a heat transfer, because everything is becoming a little bit slow now. Okay. So, now if we have to write the energy equation for the heat transfer part, what will be the basic equation? This will be this, right, U got it. This U is the same radial velocity that we got earlier, right. So, the initial conditions and boundary conditions therefore becomes T at r comma 0 is the same as T infinity, T at r comma T is equal to the saturation pressure at, this is the surface of the bubble, and T at infinity comma T will be equal to TL at infinity, got it. Okay. So, these are the initial and the corresponding boundary conditions that you have. Okay. So, what happens is that at the liquid vapor interface, you should have this being obeyed, right. So, this is at the, because this is nothing but the mass, this is rho into V, right. Okay. and the area cancels from basically from both sides. So, basically rho into V, area cancels from both sides. So, it is basically K A into the conduction flux is equal to whatever is the that heat is being used for the latent heat of vaporization. That is the essential essence of this particular story, right. Okay. So, based on these, okay, the instantaneous bubble radius okay, is shown to be okay, alpha L into T, that is the instantaneous bubble radius. Okay. Now, we can define something called a Jacob number or Jacob number, whatever you call it. Okay. So, that Jacob number is given by rho L CPL TL infinity minus T sat into PV divided by rho V into HLV. Okay. This is the Jacob number. Now, for large Jacob number, so you can see what the Jacob number is basically the liquid minus the saturation temperature divided by whatever is the latent heat. Okay. So, it is basically that. For large Jacob number, CR is basically 3 pi into J A. For small J A, we have CR equal to J A by 2. Okay. So, therefore, there are two stages. In the first stage, RT is proportional to T, which is basically what we call a linear growth regime, right. In the second stage, RT is proportional to root over T, which is basically this is inertia. Okay. This is basically heat transfer controlled. Okay. So, you will have basically two slopes, one slope like that, okay. The other slope will be something like that. Okay. Something which is less prominent. Okay. So, this is basically the linear T1, this is T half. Okay. So, this is R, this is the time. Got it. So, there are two zones, one is a linear, one is the heat transfer controlled. These two zones, basically two zones that we get over here. So, this clearly establishes the fact that so based on two mechanisms, one is the inertia and one is the heat transfer controlled, we can actually define and we can actually show that what is exactly happening to the whole process. Got it. And this is for homogeneous nucleation only. Got it. Clear up to this point. Okay. So, that is the bubble growth. So, these are all related to bubble growth, right. Now, in the case of heterogeneous bubble growth, okay. So, this is attached with a surface, right, bubble attached to a surface. Okay. So, now, the vapor bubbles attached to a heated surface, basically the growth occurs in a non-uniform temperature field, okay, to say the least. Okay. So, what Hans and Griffith did, what they did was that the bubble can grow from a nucleation site if the thermal layer adjacent to the nucleation site is thick, and they said that the bubble normally grows like a hemispherical cap. So, the bubble is like a spherical cap. I will show you the picture in just a second, okay. And the bubble can grow from a nucleation site, that is, if you recall, it is like a micro crack or a crevice, okay. If the thermal layer, if and only if the thermal layer adjacent to the nucleation site, is thick, okay. So, and we will show what that is. So, they found that RC, which is the max, and RC max comma RC mean is basically given by delta by 3, which will show delta is the thickness of the thermal layer. So, that is delta. So, it is 1 plus minus 1 minus 12 sigma T sat divided by rho v HLV TW minus T sat raised to the power of half. Okay. So, this is for saturation conditions. For saturation conditions, remember we had saturated boiling and things like that. So, saturation conditions, okay, that what will be the sizes that will be active, the maximum and minimum cavity sizes that will be active. Okay. So, now if we look at this particular presentation, we will get an idea of what we are talking about. So, Howell and Siegel, they did, and if you look at figure number 10.8, okay, they examined that how the bubble from a single nucleation site of known diameter. So, this nucleation site's diameter varied anywhere between 0.1 to 1 mm, okay, on a highly polished surface. How do these bubbles actually grow? So, if you look at it now, there are two scenarios that are possible, okay, when the cavity size, half of the cavity size essentially RC is so large that a part of this bubble actually sticks, okay, above the thermal boundary layer, which is given here, that is the thermal boundary layer thickness, got it. So, a part of the bubble basically sticks out, okay, and in the second case the most of the bubbles is actually encompassed within this thermal boundary layer, okay. So, what happens is that what they said that if the bubble is extending out, that is case number 1, if we consider this as your case number 1, then evaporation happens in this layer and condensation happens in that layer, all right. So, in the first case you have evaporation in delta and condensation in RC minus delta, okay. So, that is what you are going to have. Now, for a bubble to grow, that heat transfer due to evaporation must be greater than the heat transfer due to condensation, right, that has to happen. So, part of the bubble is evaporating, part of the bubble is basically condensing. So, based on this argument, what they showed was that your T wall minus T saturation, this temperature has to be greater than 4 sigma T sat divided by rho v HLV into delta when RC is greater than delta, got it, for a bubble to grow. So, this is for this situation, okay. The TW minus T sat must be greater than this because this has to be satisfied, okay, this has to be satisfied. Now, if the bubble is wholly inside this, which is this particular case, the bubble is wholly inside this TW minus T sat, okay, has to be greater than 2 sigma T sat divided by rho v HLV into RC, okay, and 1 minus RC by 2 delta when RC is less than delta. So, that is for this case, that is the condition for bubble growth. Okay. So, this is what for heterogeneous bubble growth first was given by Hans and Griffith, who showed one comprehensive relationship that what kind of cavity sizes will be active, okay, depending on the thermal boundary layer thickness, whereas on the other hand Howell and Siegel said they consider two extreme cases, one in which the bubble is protruding out, in the other case the bubble is completely confined within the thermal layer, and they showed for a very large variation in cavity sizes from 0.1 to 1 mm that there are two limiting conditions. When the cavity size is large, in order for a bubble to grow you need to have this relationship, for the other case you need to have that relationship. Okay. So, these are the two things that Siegel and Howell actually found out. Okay. So, we end this lecture with this, okay, before we move on to the bubble detachment. So, right now we have studied the bubble formation and bubble growth. Okay. Now, we are going to see bubble detachment, how a bubble actually detaches from a surface. This is the growth part, right, but ultimately the bubble detaches and then it goes into the main fluid, right. So, how to study that, that is will be the topic of the final lecture that we are going to do on this. Thank you.